Hey, this is Garrett and welcome back to the channel. Today I have another shop enhancement video for you today. I promise this won't be the only videos I make now, but this one I started a few months ago and it's finally time to finish it. This is the camera rig that I currently use. It has a microphone arm that reaches out and back and gives me plenty of reach around the shop. At full extension, it gives me about 55 inches of reach away from the base. There is also this handy clamp that lets me move the whole arm up to the top to get shots way up near the ceiling, or all the way down to the bottom to get shots near the ground. The last big improvement I need to make is to replace this pivot. This is the factory pivot that came with the microphone arm. You can see there just how much play there is in the pivot. I can lift the end of the arm up and down quite a bit without it staying in place, and this is really difficult when positioning the camera. I never intended to use it this long, but I just threw it on there because I needed to start using this arm. To replace this, I will use this scrap piece of aluminum and this partially completed pivot. I started working on this a few months ago, but got busy with my graver build and decided to shelve it for a bit. I thought it'd be kind of fun in this video though to give an overview of what it takes to actually run a manual mill. If you know nothing about milling machines, here's a quick overview. First, imagine your standard cordless drill. It turns on and spins a drill. Drills are good at cutting on the tips, but not on the sides. So instead of a drill, you will use an end mill. Now you can cut not only on the ends, but also on the sides as well. But this is very difficult to control manually. So you take this drill and put it into a stand to hold it. The drill is now called a spindle. Instead of a drill chuck to hold on to the end mill, I will use an R8 collet. There is a taper on the collet and a matching taper on the inside of the spindle. This drawbar runs all the way through the spindle and threads into the back of the collet. When the drawbar is tightened, it pulls the collet into the spindle and those tapers will cause the collet to squeeze down onto the end mill to hold it. There are many different attachments that can be made to fit an R8 collet. The spindle is housed in the head of the mill and can be moved up and down with an extension called the quill. To cut its shape, you'll want to move the spindle in 3 axes. Left to right, which is the x-axis, front and back, which is the y-axis, and up and down, which is the z-axis. On a manual mill, you have these hand wheels that are used to move the spindle around the part. You have dials, which will let you know how far you've moved the spindle when you're turning them. In America, typically one turn of the wheel is 1/10 of an inch. There are ticks going around that subdivide the turn of the wheel. Counting your turns and ticks will tell you how far you moved the spindle, or you can use a digital readout or DRO. This will just tell you the position of the mill. I only have one of these on the z-axis and the quill. And that is a milling machine put very simply. You'll see that there's a lot of work that goes into essentially making 4 holes. Before I start boring out the existing hole, I need to locate my mill over the center of it. I do this by using a dial indicator that is held in an arm in the spindle. An indicator isn't used to measure absolute values, but rather relative values. What this means is I want the dial to read the same value on both sides of the hole. If the dial reads the same on both sides of the hole, then the distance from the center of the spindle to the side of the hole is the same on both sides, which indicates that the spindle is centered over the hole in that axis. I zero the dial indicator for easier reading, and with the spindle centered on the y-axis, I will now work on the x-axis. This axis is a lot easier to center. I pick a side and simply move the spindle until it reads the same zero from the last axis. Sweeping around the hole, I confirm that the spindle is centered and lock the x and y axis so they won't move. Removing the dial indicator and swapping out the 3/8 collet for a 1/2 inch collet, I load in a 1/2 inch drill to clear out this hole. The hole in this block goes all the way through, but I need to make sure it is at least 1/2 inch in diameter for the next tool, which is a boring head. This little boring bar goes into the boring head and is what does the actual cutting. I need a minimum of a 1/2 inch hole started so that it can pass all the way through. I move the boring bar off to the side, lower it down using the quill until it touches the aluminum, and zero the DRO in the quill. Now when I'm using the boring bar, I will know exactly how far down I've gone from the top of the hole. What I did there was just to touch off the inside of the hole so I know that the boring bar will start cutting on the first pass. Starting the mill, I go for that first pass and bore the hole in one go all the way down to 3/4 of an inch, which frankly was a bit much for my mill. I want this hole to be a clearance fit, so I'll measure the diameter of the pivot, add about 25 thou to that, lock my calipers, then transfer that measurement to a telescoping gauge. Then I can take that gauge and check the bore, and I can see that there is well over 25 thou clearance, which should be perfect. That is the exact opposite way you typically use the gauge. Usually the telescoping gauge is sized to the internal diameter of the hole. Then when you take it out, you measure that with calipers or a micrometer so you know the size of the hole. But I digress. On this mill, the quill can only extend about 2 inches, and the block of aluminum is just under 2 3/4 of an inch thick. Instead of trying to make one hole that goes all the way through, which would be very difficult, I opted to make this top portion a clearance hole and then lower my mill down to just shy of 3/4 of an inch. That way the boring bar can reach all the way through to the bottom of the block. Once again, touching off the boring bar on the side of the hole, I lock off the grub screw, turn on the mill, and start boring out the rest of the hole. To make the next pass larger, I loosen the grub screw, adjust the position of the boring bar with the adjustment screw, retighten the grub screw, turn the mill back on, and I'm ready for a second pass. This process repeats over and over and over again until the desired diameter is reached. This is the last pass, and the hole should now be 1 to 2 thousandths over the size of the pivot, which I confirmed with the telescoping gauge used the right way, but forgot to film it. After moving the boring bar out of the way, I can check the fit with the pivot, and it's perfect. I take this block out of the vise and rotate it 90 degrees in the y-axis of the mill. When a vise clamps onto a workpiece, it will typically push one or both sides up. As you can see, it isn't resting on the front parallel. A few whacks with a hammer will seat the aluminum down onto the parallel so it won't move. Checking the rear parallel, the same process is repeated for the back side. Then the vise is tightened a little bit more for good measure. The next two holes I'll be making are for the mounting screws that will connect this to the clamp on the camera rig. Mills are fantastic tools. They have all the dials and gauges that can make extremely precise parts, however, they don't automatically know where your part is. To figure this out, there are many different methods you can use, but I'm going to be using an edge finder. Essentially, this is a tool that is precision ground with an upper section that is held in the spindle of the mill and a lower section that is connected with a spring. You bring that edge finder up to the edge of your material, and once it kicks out, you know that the edge of the edge finder is at the edge of your material. However, it may not be perfectly at the edge. So what I do is I back off the hand wheel and move the mill until it is 2 thousandths away from the 0 mark. Then I look at my edge finder to see if it's kicked out. If it hasn't moved, I'll move the hand wheel half a tick, which is 1/1000th of an inch, and take another look at the edge finder, and you can see that it is kicked out. So clearly my 0 is not correct. I'll adjust my 0 back to the new position and repeat this process again. 2 thousandths out, check to see if it looks good. 1 thousandths out, check to see if it looks good. Go to the point where the line on the little arrow mark is right next to the line for the 0 and look up to double check it looks good. Then move to the 0 and it should be kicked out. For me, this is enough confidence that I have accurately picked up this edge of the block. I can now come over to the front of the block and repeat this process again to pick up the front edge. A quick side note I forgot to talk about earlier, the smaller section of the edge finder has a diameter of 2/10ths of an inch. With one turn of the hand wheel being 1/10th of an inch, this means that once you find the edge of your material with the edge finder, one turn of the hand wheel will place the spindle perfectly over the edge of your material. Now I know where the aluminum block is in relationship to the mill. I move the mill to the 0 point on the X and Y axis, which places the spindle perfectly over this corner. I want to make this hole 1.18 inches from this corner in the y-axis and 0.604 inches in the x-axis. Starting with the y-axis, I count the hand wheel revolutions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1 inch, 1, 20 thou, 40 thou, 60 thou, 80 thou. Moving over to the x-axis, I count 1, 2, 3, 4, 5, 6, 2, 4. The mill is now in position to make the first mounting hole. I swap out the edge finder and call it for a drill chuck and secure the number 7 drill in the chuck. A little bit of cutting oil makes this job a lot easier, and I can start drilling this hole. I run into the same issue with this drill as I did with the boring bar, where the quill bottoms out before it has gone all the way through the material. To counteract this, just like with the boring head, I lower the head of my mill down so the drill bit starts out inside the material and add a lot of oil to keep the drill bit cool since it'll be rubbing against the aluminum the whole time it's on now. I want to get this done quickly, so I start drilling until the drill pops through the bottom of the aluminum. There needs to be a countersink for the head of the screw that will go inside this hole. I'm going to cheat a little bit and do something that's not recommended. Instead of swapping out my drill chuck for an R8 collet, keeping in mind I have another hole I need to drill and countersink and another hole I need to drill after that, so to save time and effort, I'm just going to hold the end mill into the drill chuck. Drill chucks are not designed to be pushed side to side and can actually come apart, but I'm just going to be plunging this down to make a countersink, so I think it should be fine. But typically an end mill in a drill chuck is a no-no. I touch the end mill off on the top of the aluminum so I keep track of how deep this hole is and start the countersink. This countersink interacts with the large pivot hole I made earlier. I knew this was going to happen when I designed it, so I just had to make sure that the countersink was deep enough that the head of the screw would not interfere with the pivot. After reaching 1.5 inches deep, the countersink is finished. I'll swap out the end mill for the drill and move the mill back to the 0 position on the x-axis. I don't need to change the position of the y-axis since the two holes share the same position. When positioning the mill, I almost always start off at the 0 point. It's very easy to lose track of where you are and mill subsequent holes in the wrong location. This is one of the great advantages of a DRO. It will just tell you where the mill is. I'm once again counting the hand wheel rotations to 1.7 inches, then counting the ticks on the hand wheel to reach 1.754 inches. I'm ready to drill the second hole, which follows the same steps as the last hole. Drill down until the quill bottoms out, lower the head of the mill, finish drilling the hole all the way through, swap out the drill for an end mill, and mill the countersink down to 1.5 inches deep. There is one final hole I need to make. Similar to the pivot on the small vise I made back in 2021, I want a handle just like this one when tightened will lock the pivot in place. I get a reprieve from counting since the position of this hole isn't critical. I'll move my mill to right about there and call it good enough. This hole will go all the way through the aluminum just like the last two holes, but this will be a threaded hole for a section of 1/4-20 all thread instead of a clearance hole for a screw. I only want the bottom inch or so of this hole to be threaded, so I swapped the number 7 drill for a 17/64 drill and drill all the way down to an arbitrary 1.5 inches, which is over halfway through the aluminum. That completes the work on the mill. I hope this gave you a better understanding of what it takes to use a manual mill, even for something as simple as making 4 holes in a block of aluminum. But there's still more work that needs to be done. To tap the bottom of that hole, I will use one of my all-time favorite tools, which is this tap wrench from Grizzly. This wrench can hold up to a 1/2 inch tap, and it goes into this guide that makes it almost impossible to break a tap. From my experience, the number one way to break a tap is to not start it off straight in the hole. This wrench and guide combo makes that almost impossible to mess up. I've even made aught-80 screw holes in 410 stainless steel without breaking a sweat. If I'm tapping a hole, I'm almost always using this wrench. To be able to make the aluminum clamp onto the pivot, I will need to cut a slot just like this, which is just the excuse I need to use my power hacksaw. There is one issue though, and that is that this block is too small to be securely held in the vise. This calls for another one of those don't do what I do moments. I'm going to extend the vise first with these 2 strips of aluminum for the bottom of the vise. This steel bar will extend the fixed jaw. This scrap steel will keep the vise from racking. And this piece of steel will extend the movable jaw. With the vise jaw extended, I can place my aluminum block in it, line up my center line to the saw blade, tighten the vise, start the saw, and send it on its way. This thing is so much fun to use. It's loud, it's smelly, it's big, it's ugly. It just seems how old machines are supposed to be. It's really unfortunate I don't get to use this as much as I would like. There's a little bit of a pucker moment here where the saw blade is about to drop from the top portion of the aluminum block to the bottom portion. Thankfully nothing shifted, which is really a testament to that makeshift setup I did to extend the jaws. I was a little or a lot worried that the aluminum would be knocked out of the vise and ruined. I don't want to cut all the way through this aluminum though, so I keep an eye on the back side of the block, and when there's about 1/8 to a 1/4 inch of material left, I stop the saw. The pivot block is now complete, which means I can move on to finishing the pivot. What I've done so far is to taper this end for easier insertion into the pivot block. I turn this step that fits perfectly into the steel that would be welded on for a collar. The hole in the center where the base of the microphone arm will go was already there from a previous project. I clamp the collar onto the pivot with just enough space that I can get in there with my TIG welder and do a few tack welds to hold it in place. Taking off the clamp and making the final tack weld, I grab a piece of welding rod and start welding the 2 pieces together. I do this in 3 sections between the 3 tack welds, just to make it easier. I'm no welder, so if you're looking for welding advice, unfortunately this isn't the channel for you. After the pivot cools off, I mount it in my lathe to clean up the weld and the outside of the collar. To be frankly honest, this is more for aesthetics than for any real mechanical reason. However, I like the tools I make to look nice, especially if the extra effort isn't that much. It takes a few passes with the lathe to clean up the weld. Making a final pass on the face of the collar, I am stunned by how good the surface finish is. Cleaning up the outside needs to be done carefully. The carbide tool I'm using does not do well with interrupted cuts, and will likely chip if I don't take this part slow. After making the final pass on the collar, I grab a file and make some chamfers on both edges of the collar. I switch out my turning tool for a boring bar. There is some weld that made its way into the hole that needs to be cleaned up. I make light passes until I feel the cut go from an interrupted cut to a continuous cut, which tells me I have now contacted the original 1/2 inch hole. To connect the pivot to the microphone arm, I'm going to fill the hole with epoxy with the base of the arm inserted. Once cures, this should make an almost permanent connection. The green tape will keep the epoxy from running out the bottom of the pivot. When trying to figure out how I was going to hold the pivot while letting the glue cure, I realized I could just use the pivot block in a vise because it was literally designed to hold the pivot. I disassemble the camera rig, grab some epoxy in a mixing cup, and measure out enough epoxy to fill the hole completely. I'm using 12-hour epoxy mainly because I need to get rid of it. It's getting a bit old, and it's supposed to be better than 5-minute epoxy, so it's a win-win. After thoroughly mixing the epoxy, I pour it into the hole of the pivot before grabbing the microphone arm and seating the base into the epoxy. Some epoxy leaked out, which I'll wipe up with a paper towel and get the final residue off with a little bit of acetone. From here, I'll leave it overnight to cure. When I come back the next day, I'm dying to see how it works. The arm pivots smoothly and feels so much better. There's almost no play in it either, which is exactly what I wanted. Finally, I can remove the pivot that came with the microphone arm, the angle iron that the old pivot was clamped onto, this other piece of angle iron that helps the clamp stay secured. I'm replacing it with this angle iron, but I'll figure out later how to attach these permanently. Grab the pivot block, drop in the mounting screws, and affix the pivot block to the clamp. Before I put the arm into the pivot block, I grab some grease and apply a good amount to the pivot. This will keep the aluminum from galling, and it will also help it turn smoothly. To assemble the camera rig, I take my arm and put it into the pivot block. My fluid head and phone holder are threaded on next. Remember that all thread I was talking about earlier? Here it is. After cutting it to length, I will apply some blue Loctite to the thread so it won't come loose. Adding this locking handle completes the camera rig. The pivot spins freely, and with just a small turn of the handle, it will no longer spin, and actually moves my entire camera rig, which has about 40 pounds of counterbalance at the bottom. It's also much stiffer now. If you remember from before, I could move the camera arm up and down quite a bit without it staying in position. There's still some play, which comes from the actual linkage of the arm itself, so there's not really much I can do about that. But this is such a vast improvement over the off-the-shelf pivot I was using before. There is nothing left to do but to mount my phone into the rig and start cleaning up the mess I made. This is an improvement that has been a long time coming, and now that it's finally done, I wish I would have done it sooner. All these different shots were so much easier to set up with the new pivot. Thank you so much for coming along with me on this build, and I can't wait to see you again the next time I'm in the shop.